Hello. In this video I want to talk about solving a trigonometric equation by inspection. And by inspection I mean just looking at the graph, all right, and seeing where the two equations intersect. All right, so let's take a look at the first one. Suppose I'm looking to solve where is y equal cosine x, and here's your cosine. Where is that equal to 0? All right, so essentially what you're saying is I have y equals cosine x, and I want to know where y is 0, right? Now it turns out, we're going to find out that the solution is going to be x equal to, the first solution you get plus k times the distance between the two consecutive solutions, any two consecutive solutions. So what I want to look at then is, where's the intersection where I have y equals 0, right? So this is y equals 0. And here's y equals 0, right? Here's y equal 1, y equal 2, y equal -1. So if you just kind of dash this in, where's y equals 0? It's going to look something like this, right? And I want to know specifically where do the two graphs intersect, cosine of x and y equals 0. So it looks like right here, there, here, there, here, and here. So far what I have are, it looks like multiples of pi over 2, right? So you got pi over 2, 3 pi over 2, and the next one will be 5 pi over 2, and so on. Negative pi over 2, negative 3 pi over 2. So let's go ahead and write those down. So I have negative 3 pi over 2, and then I have negative pi over 2, then pi over 2, and then 3 pi over 2. And it goes on and on. So what we could do is we could write dot, dot, dot to mean infinitely, and then this way also dot, dot, dot. It's not the most pleasant way of doing it, but it's definitely one way you can let somebody know. This goes on infinitely, right? So what's happening is on the unit circle, we're here, say, for example, at pi over 2, right? So we started at 0 and began our first angle, our first solutions at pi over 2. The next one is going to be at, for example, 3 pi over 2 if I keep rotating in the positive direction, right? So I go from here to here. And I rotated, how far did I go when I rotated from pi over 2 to 3 pi over 2? And then we'll figure out that distance. So how far is this distance from pi over 2 to 3 pi over 2? Well, here's two consecutive solutions. So let's take end minus beginning. So 3 pi over 2 minus pi over 2 is 2 pi over 2, or pi. So it looks like the distance from here to here is pi. Well, is that going to be true all the way, for every two consecutive solutions we use? So let's say we look at the distance between negative pi over 2 and pi over 2. Let's look at that. So let's do distance between negative pi over 2 and pi over 2. So here, end minus beginning, so pi over 2 minus a negative pi over 2, again gives me 2 pi over 2, or pi. So it looks like we have the distance, we found that the distance here was pi, and now we looked here also and said, looks like that's also pi. And if you keep doing this, if you look at the distance between negative 3 pi over 2 and negative pi over 2, you're also going to get what? Pi, of course, right? So what's happening is every time you rotate, once you start on a solution, every time you rotate pi, you land on another solution. So now that I'm on 3 pi over 2, when I rotate pi, I'll be at 5 pi over 2, I'm going to land on another solution. So the only difference of looking at this on the unit circle versus a graph is that you could imagine that at 0, we were to pop this apart, right, this circle apart, and just lay it out as an infinite line. And that's what we have here. So what's going to happen is we're going to have an infinite number of solutions, and that's what we started to see here when it's just repeated. Why? Because you're going around the circle. And so, of course, you're going to land on the same spot many, many times. And there's your repetition, right? So let's take a look then. How do I write this? Do I really want to write this as let's see here. So let's go ahead and put our distances here, pi. Do I really want to write this way? No, we think there's an easier way. So what happens is, if I pick a solution, so here's where I'm going to help you learn how to write the solutions in a slightly more elegant way, and it's quicker. All you need to do is start at a solution. So for example, let's say usually you start at the first positive solution that's closest to 0. That's generally what we do. The first, generally, we pick our first solution to be the first positive solution closest to 0. All right, so the smallest positive solution. All right, so in our case, that would be pi over 2. So now let's take a look and see if we can write this out. So at pi over 2, and what happens is to get to the next solution, what do I need to add? Or what's the distance? If I start at pi over 2, the distance to the next solution is pi. So if I add 1 pi, I will get what? 3 pi over 2. Well, once I'm at 3 pi over 2, I'll tell you right now, the next solution is going to be at 5 pi over 2. Right. So if I take 3 pi over 2 and add another pi, I'll get to 5 pi over 2. And so on and so forth. So essentially, if you start at your solution, your first solution, and you add k pi, where k is an integer, and remember, an integer is a whole number that is positive, negative, or 0, so just no fractions or decimals. Then that's how you can capture all your solutions. All right, so that's what your general format will look like. This would be my solution, pi over 2 plus k pi. So when k is 1, so if I now start and I say, okay, let's say k be 1, there's how I get my 3 pi over 2. So that's k equal 1. Well, what if I let k be 2? Well, now I have pi over 2 plus, now I'm going to have to add 4 pi over 2, and I'll get 5 pi over 2. So that's k equal 2. Can I get the negative pi over 2? Sure. I can say pi over 2 plus a negative 1 times pi. It's going to be pi over 2 minus 2 pi over 2 gives me my negative pi over 2. So that's k equal negative 1. If I just want pi over 2, I'm going to let k be 0. So I can capture all of them. The only difference here is, where do you start? So we decided to start here, and then when I add 1, I'm here. K equal 1, I'm here. K equal 2, I'm here. K equal 3. If I go the other way, k equal negative 1, I'm here. K equal negative 2, I'm here. That's because we started here. So what do you think would happen if instead I started, let's say, at 3 pi over 2, and I wanted to describe the rest of the solutions? Well, I would still use, so if we started at negative 3 pi over 2, my solution would look like, solution set, negative 3 pi over 2 plus k pi. And that looks an awful lot like pi over 2 plus k pi, because remember, we're looking for a solution plus k times the distance between two consecutive solutions. Well, the distance between the any two solutions in this, when we're trying to solve cosine x equal to 0, the distance is the same. It's just, where do you want to start with your first solution? So if I want to start here at negative 3 pi over 2, I can see on the graph that if I wanted to say, hey, I want this solution over here, pi over 2, k would have to be what? It's kind of, you can think of it, how many hops do I have to get? Here's for the first hop, k equal 1. Here's the next one here, k equal 2. If I put k equal 2, then I'll get this pi over 2. Let's just try it. So if I say let k equal 2, negative 3 pi over 2 plus 2 pi. negative 3 pi over 2 plus 4 pi over 2. And that's going to be pi over 2. So there you are. So as essentially the k tells you how many times you're going to hop away from your solution, the one that you pick. It tells you in what direction, positive or negative, and then how many times do you hop away. So there's how many times you have that set of that distance. So here's once, twice. Okay. So if I wanted to start at negative 3 pi over 2 and I want to describe 5 pi over 2, I'd be at 1, 2, right? Then 3, 4. K would have to be 4. So anyway, I'm just showing you this because when things get more complex, it's a little harder to see this, right? Sometimes it's a little harder to see. So let's try one other one, and what I'm going to do is have you look at it, solve it by inspection, like find out where your solutions are, then pick, well actually find your solutions, then find the distance between two consecutive solutions, then pick a solution, and probably the best one is the one closest to 0 that's positive, and see if you can write that little formula, x is your solution plus k times the distance. So go ahead and pause the video and try that. And now what I'm going to do is, assume you paused. So here what I'm doing is saying that I'm solving for y equals sine x. So here's my basic graph, y equals sine x. And then also, where is it equal to 1? Where is y equal to 1? So here's y equals 0, y equal 1, y equal 2, right? Y equal negative 1, negative 2, that kind of thing. So you're really looking for this, right? Where does this intersect? Where does the sine function intersect with y equal 1? So it looks like it intersects for the x values here, negative 3 pi over 2, and then let's see here, pi over 2, and then here, 5 pi over 2, right? So those are your, here's 3 consecutive solutions. So let's go ahead and write those out. So we have 3 consecutive solutions are, we had negative 3 pi over 2, then we had pi over 2, and then we had 5 pi over 2. Okay. Now let's find the distance between them. 2 consecutive ones. Distance between, for example, pi over 2 and negative 3 pi over 2. Well, remember, it's end minus beginning, so, and we always, so as you're reading from left to right, pi over 2 is further than negative 3 pi over 2, so this is my end minus beginning. So here's pi over 2 minus a negative 3 pi over 2 is 4 pi over 2, which is going to be 2 pi when I reduce it. All right, so we know that distance from here to here is 2 pi. Let's go ahead and do that in a different color. And let's see if it's continued from pi over 2 to 5 pi over 2, right? So again, end minus beginning, so let's find that distance in between pi over 2 and 5 pi over 2. We'll do 5 pi over 2 minus pi over 2 is 4 pi over 2, which gives me 2 pi as my distance. So yes, same distance, right? And so let's mark that over here. So at this point, I'm ready to say, okay, I get the basic pattern, right? It's a pattern that my solutions are occurring at an equidistant apart. So, and that distance is 2 pi. So all I need to do is start on one of the solutions. It doesn't matter really which one, all right? And then add multiples of whole number multiples of 2 pi in either direction, positive or negative. Now, most people or most books, even though you could use any solution that you want to start at, I could start at 5 pi over 2 if I wanted to. Most books will start again at the first positive solution closest to 0. So what they'll do is they'll say the solution set is x equals pi over 2 plus k times 2 pi, right? So here's your solution, pi over 2 plus k times the distance, 2 pi, all right? And that's actually fine, but again, most books really like to make it a little prettier. So remember, these are just being multiplied, right? In the same way that I can say 3 times 2 times 5 is the same thing as 5 times 2 times 3 is the same thing as 2 times 3 times 5, right? It doesn't matter the order in which I multiply those. What I can do here is say x equals pi over 2 plus 2k pi, right? I'm just multiplying these. These are all. So that's the order they seem to like to see it in, where the k's in the middle, all right? So that's just what we're going to be doing, is solving trigonometric equations by inspection at first, just so you can understand it. Then we're going to learn how to solve it algebraically and graphically, and there's an awful lot of techniques and an awful lot of videos for you to watch. And I just want to mention one more point, that sine and cosine are particularly used for modeling in the real world when you have repetitive patterns. So for example, let's say I'm breathing and I'm measuring how much air is in my lungs over time. Well, my lungs expand and contract and expand and contract and expand and contract, and they do so pretty rhythmically and pretty much to the same amount. So that's the kind of thing that Trig is really good at modeling in the real world. Or maybe you could be talking about the hours of sunlight during a particular season, you know, in a city. And yeah, it varies depending on the time of the year, but if we're talking about a certain season, over the years, it's usually the same. And so again, you're looking at cyclical things. And again, all this is because what you're really doing is looking at movement around the circle, and that's repetitive, right? All right, thanks so much for listening.